Recall the two main kinds of web request, GET and POST. GET requests are meant to be reads of the server state. As such, they are not intended to affect modifications to that state. Nevertheless, they often do just that. With this in mind, consider the URL to the banking website shown here. Suppose a user is logged into this site with an active session. What if an attacker is able to trick the user into visiting this link? The outcome for the user is not good, an unintended bank transfer out of his account. The question is, what would convince a user to visit this link?
So here's how this could happen. Suppose the client is logged in to the banking website and at the same time is surfing the internet and ends up at attacker.com. Attacker.com returns a page back to the user, and that page contains this tag, where the tag includes a reference to the URL that we saw before. Now the browser, upon seeing the image tag, will automatically visit the URL to obtain what it believes will be an image. So it will go to bank.com and send the request. Now, normally, if the user was not logged into the banking website, bank.com would reject the request because the user was not authenticated. But if the user happened to be logged in at the same time as when visiting attacker.com, then this request will be accompanied by the session ID that includes the cookie that says that the user was authenticated. And as a result, bank.com will dutifully perform the request.
This kind of misdirection attack is called a cross-site request forgery, or CSRF. The target of the attack is a user with an account on a vulnerable server. The goal of the attack is to issue requests on the user's behalf that look to the server to be legitimate. To ensure legitimacy, the requests are issued from the user's browser, which will send along the needed session cookies. For the request to come from the browser, the user must be tricked into clicking a link while logged into a sensitive site. In the previous depiction, this happened when visiting a malicious site which sent a request to a URL embedded in an image tag. The user could also be tricked to click a link in a spam email, which will get sent by the browser. The link could be disguised, for example, by email formatting to look benign. CSRF works because certain sorts of requests to the vulnerable site have the same structure, minus the session information. Let's look into this in more detail.
So how can we protect against CSRF attacks? One way to do it is to pay attention to the referrer field that's set by the browser when it sends an HTTP request to the server. Recall the request that we saw in the example earlier in this unit, where we clicked a link on the reddit.com site. Here we can see that the referrer is filled in with the original page on which that link resided. What a server could do is check that when it receives a request, especially one that's sensitive, that the referrer field only includes URLs for that site, or from any trusted location from which the link could have been generated. In our example, the referrer should not include attacker.com and it would reject the request. So only the pages that a user could legitimately reach should be allowed as referrer fields. The problem here is that the referrer field is optional. Not all browsers send it along. One way to deal with this problem is to use what's called lenient referrer checking. That is, we should block requests with a bad referrer, for example, attacker.com in our prior example, but allow requests with no referrer, for example, because the browser just doesn't include it. So then the question is a missing referrer always harmless, assuming that the browser is legitimate? Unfortunately, the answer is no. Attackers can be clever in sending redirect requests and other protocol messages to cause the referrer to be removed. For example, it can bounce a user off an FTP page that the attacker controls, and the FTP request will not include a referrer header. The attacker could also exploit a browser vulnerability and hack the browser to not include the referrer field, or could mangle the web request in transit by snooping on the link. Another approach is to use secretized links. The idea here is similar to hidden form fields where we used capabilities. Here the hidden form field will include a secret that the attacker has a difficult time guessing. So recall that the attacker relies on the cookie already being present in the user's cache so that when the request to the remote site is initiated, the cookie goes along with it. But the attacker does not know what the contents of the cookie are. It doesn't know what is expected on the page that would normally allow such requests. So if in that page we can embed a secret that the attacker wouldn't know, and the server only allows the request if that secret is included, say as a hidden form field, then we protect against the attack that we saw before, that is, attacks initiated indirectly from a remote site. We can even make the secret equal to the value in the session cookie because, as I said before, the attacker has no way to see the cookie. The attacker can only cause the request to go out without knowing exactly what that request contains. And web frameworks help here. For example, Ruby on Rails is a web framework that makes it easy to write multi-tier web applications, and Rails automatically embeds such secrets in the links that it generates for the web pages of the sites it produces.